Hello, hi everyone, welcome back to the series. So in this video lecture, we'll be solving this problem, company queries. I hope you're learning something from this series and let's solve this problem. So in this problem, we have a company which has n employees and the company forms a tree hierarchy where each employee has a boss except for the general director. The general director do not have any boss. The task is to process Q queries of the form who is employee X's boss, X levels higher up in the hierarchy. Fine, so we are given a tree which has n nodes. They are numbered from 1 to n, and basically the nodes represents the employees of the company and the tree represents the company. Okay, so let's take an example. Let's better understand the problem statement using the example given here in the problem statement. So the example is like this. We have two integers, the number of nodes and the number of queries. In the very first line, the two integers n and q. Then we have n minus 1 space separated integers, which basically represents the boss for each employee starting from employee number 2 till employee number n. Like here in this case we have 1 1 3 3. That means for node number 2 and node number 3 the boss is node number 1, and for node number 4 and node number 5 the boss is node number 3. Okay, then we have q lines, means we have three lines or representing three queries where each line has two integers x and k, and we want to ask who is the employee x's boss, k levels higher up, right? Like here, who is the who is the boss of employee number 4, 2 levels higher up, right? If the boss does not exist, in that case we print -1. So let's understand this example which is given in this problem statement. So node number 1 is the boss of node number 2 as well as node number 3. Then we have node number 3 as the boss of node number 4 and node number 5. Okay, so this is the given tree. This is the company that we have which has 5 employees. So let's answer the queries. The very first query is 4 1. So what does this query ask? Who is the who is the parent or ancestor of node number 4 one level up, and that is node number 3. So for this query the answer is 3. Let's see the second query. The second query is 4 2, which asks us what is the ancestor of node number 4 2 levels up. So 1 level up it is 3, and then 2 level up it is 1. So the answer is 1. It's 3 and it's 1. The last query is 4 3. Yes, it's 4 3. Means who is the ancestor of node number 4? 3 levels up. So 1 level up it is 3, 2 levels up it is 1, and then 1 more level up we do not have any ancestor. So we put -1. So for these cases, we have -1 as the answer. So what is the strategy to solve this problem? How can we solve this? How we can think about these type of questions? So the very first and the naive approach which comes to the mind is to store the parent for every node of the tree. Okay, so we store the parent of every node of the tree in a parent array. So we prepare a parent array like this. So for node number 1, we have parent as -1. For node number 2, the parent is 1. For node number 3, the parent is 1. For node number 4, the parent is 3. For node number 5, the parent is 3, right? These are the parents for the nodes. So that's what we need, right? So what we can do is, let's say I want to answer this query, which is 4, 1. So start from 4 and move to the parent of this node, which is 3. Okay, so print it because we just have to move once. We just have to move one level up. Let's answer this query, which is 4, 2. So start from 4, move to its parent, which is 3. The element present at position number 4 is 3. Then move to the position number 3 here. Okay, so move to this position here like this. And what is the element present at this position? It is 1. So we have moved 2 levels up from 4 to 3, then from 3 to 1. So the answer is 1. Let's answer third query. Start from 4, move to its parent, which is 3. Now from 3, move to its parent, which is 1. Now from 1, move to its parent, which is -1. So we have to move 3 levels up from 4 to 3, 3 to 1, 1 to -1. So -1 is my answer. Fine. So this is the very first strategy to solve this problem. We do not have to do like much in this strategy. We just store this array, and this array is basically given in the input itself. We can see that here. We are given this 1, 1, 3, 3. So we store this array right from the input, and then all we have to do is just traverse how many times? It's k, right? Yeah. So we have to traverse k times for every query while starting from the node which is x, the x node which is given here. So like what I have done here. What is the time complexity for this approach? So for any query, I may end up traversing all of the nodes of the tree, because let's take this type of tree. Node number 1, then node number 2, then node number 3, then node number 4, and so on. Okay, so take this type of tree, and in this type of tree, this is a skewed tree. Let's say I want to move to node number 1. I am starting from node number 4. So move one level up to node number 3. Now move one level up to node number 2. Now move one level up to node number 1. Okay. So in this case, I had to jump to all the way up to the root node. And that's why the time complexity in the worst case for any query becomes big of n, where n are the number of nodes in the tree. And we have q such queries in the worst case. So time complexity, the overall time complexity becomes big of n into q. And we can see the order of n and q is up to 10 raised to the power 5. So this will give me 10 raised to the power 5 into 10 raised to the power 5, which is like 10 raised to the power, the operations of order 10 raised to the power 10. And we know that the number of operations in 1 second are 10 raised to the power 8. The computer performs these many operations in 1 second. That is going to give us like 100 seconds. The program is going to take 100 seconds to execute for these higher constraints when where n and q is of the order of 10 raised to the power 5. So in the extreme constraints, for the extreme test cases, the time taken would be 100 seconds, which is beyond the time limit. The time limit, you can see that it is 1 second here, right? The time limit is 1 second. So 1 second and 100 seconds, is a lot of difference between them, and that's why this approach will not work for the constraints given in the problem statement. So we have to find a better approach to solve this problem. So let's see that better approach. Now the better approach is basically, usually we solve these type of problems where we have to jump in a tree like this. We have, or we want to find like the lowest common ancestor of two nodes which we are given. In these type of problems, the technique that we use is called binary lifting. Okay, so this is a technique which we will be using to solve this problem. So let's see how. Let's first let me first give you the basic idea of binary lifting, and I will explain this technique in detail in some other video or some blog. In this For this video, just let's understand the basic idea of how binary lifting works, right? I will attach the resources to learn this technique in deep if you want to learn them, if you want to learn this technique. Otherwise, you can also use it as a black box. Okay. So the technique is simple. Let's say I want to jump from node number 4, k levels up. Let's say the levels are 3. I want to jump 3 levels up, right? Let's just take a little, let's take this type of tree when we have 6, and now I want to jump from node number 6 3 levels up. Okay. So instead of jumping one by one, like from 6 to 4, then from 4 to 3, then from 3 to 1, what I'm going to do is I'm going to take the jumps like this. Take the jumps of size which are of 2's power. So 3 can be represented like this. 3 can be represented like 0, 0, 2. This is the binary representation of 3. That means if I want to take jump of size 3 from node number 6, what I can do is I can jump from node number 6 to the node which is 2 levels up, because 3 is nothing but 2 raised to the power 1 plus 2 raised to the power 0. Means the first jump is going to be of size 2, the second jump is going to be of the size 1, because 2 raised to the power 0 is 1. So from node number 6, take a jump of size 2. From node number 3, take a jump of size 1, and will reach node number 1. How it will improve how this type of jumping is going to improve our time complexity? Let's take a better example to understand the difference between the time complexity when we use this technique, right? So let's take this example. Let's extend this tree. We have node number 7, or let's just say I start from some node. Let's say the node is some hypothetical node, let's say, or let's just draw the tree. Let me draw the tree. Let's just from node number 7, then we have node number 8, then we have node number 9, like this. Okay, so we have 9 nodes. We have nodes till 9, and let's say 2, 3. We also have a node which is node number 10. 1 2 3 4 5 6 7. Okay, so let's say I want to start from node number 10. This is the node, and for this node I want to find its ancestor, which is 7 levels up. Okay, so what I will do is, instead of making 7 jumps from 10 to 9, then from 9 to 8, 7, 6, 4, 3, 1, what I'm going to do is I am taking the jumps of size, because I will take the jumps of size which will be 4 plus 2 plus 1, because find the largest power of 2 in this 7, that will be 2 raised to the power 2, because 2 is the largest power, because 2 raised to the power 3 becomes 8. Now the remaining number is 3. So find the largest power in 3. It is 2 raised to the power 1. Remaining number is 1. Find the largest power for 2, which is 0. So this is how we can represent 7. It is equivalent to representing 7 like this in that binary number: 8, 4, 2, 1. So we have this bit set, this bit set, and this bit set, which is 0th, 1st, and 2nd, represented by these exponents. Fine. That means the size of the jumps which I will take will be 4, then 2, then 1. So from 10, I will jump to 1, 2, 3, 4. I will directly jump to node number 6. Then from node number 6, I will directly jump to node number 3. Then from node number 3, I will directly jump to node number 1. So the jumps that I have taken is 3. The jumps taken are 3, and if I basically if I use the parent array, the previous strategy, the jumps would have been 7. So 3 is way better than 7. Basically, the number of jumps reduces to log to the base 2n. So from n, the jumps reduces to log of n. That's the improvement if I use this type of technique. If I use the binary lifting technique to solve this problem. Okay. Now the implementation details, how we're going to implement this strategy, how we basically build the proper data structure for this binary lifting, will be explained in some other video or blog. For this video, just think about binary search as a black box, and you will learn when we'll code this technique. And let's just see how we can solve this problem. The problem is simple. Just use this binary search, this binary lifting technique to find the to reach to the appropriate level. Okay. Now what we're gonna do is, basically here we know that, like, in the binary lift technique, we use an array, we use a 2D array. So we use a 2D array up of dimensions n, m, where m is log of n to the base 2. This is m, right? This is my m. Now up of I, j, this represents the 2 raised to the power jth ancestor for node I, right? This is what this element represent. So for node number I, the the 2 raised to the power jth ancestor is stored in this position, right? So let's see how we build this array. Okay, let's take the same tree which we are given in the problem statement. Node number 1 connected to node number 2, then node number 3, then from 3 we have node number 4, then from 3 we have node number 5, right? So this is the tree which we are given. Let's try to build that up array. The dimensions of the up array for this tree would be, will have 5 rows. Okay, 1 2 3 4 5 rows, and will have log 5 to the base 2, ceil of log to the base 5, so it's ceil of log 5 to the base 2, and that would be 3, right? Because 2 raised to the power because it requires so we'll have 1 2 3 4 and 5. These are the nodes, and here we'll have our we'll have one more column, three. Okay, so this so I will use this type of array. This will be the dimensions of the array. Now let's first store the immediate parents. So for node number 1, the immediate parent is -1. For node number 2, the immediate parent is 1. For node number 3, the immediate parent is 1. For node number 4, the immediate parent is 3. For node number 5, the immediate parent is 3. How are we going to do this? This can be done using DFS. So we know how we perform DFS. We pass in the node from where we are calling the DFS. Then we call the parent node as well. So basically in this array, when we are performing the DFS, I will be storing the parent node for each node. For node 0, up node 0, that represent, for this node I want to store the 2 raised to the power 0th parent, that is the first parent or the immediate parent, and that will be nothing but the parent which we have here, this one, right? So that's what we'll be doing. Okay, now we are done. We have stored the immediate parents of each node. Now how will basically store the other ancestors for each node. Like for node number 4, we have node number 3, which is here. Then we have node number 1 as well. That can be done easily by basically traversing over each node, and then for each node traverse over each of these columns. Like let's start from node number 1. So for node number 1, I want to find, first of all I want to find, we are given the 2 raised to the power 0, which is the immediate parent, which is -1. I want to find the second parent, the fourth parent, and the eighth parent. So I will start traversing from 1, then 2, then 3. So start traversing from 1 till 3. So to find the up of 1, 1, what I need, that is the second parent of node number 1. I need the first parent of node number 1. So for up, I need so basically if I know the first parent of node number 1, then I can find the second parent of node number 1, because the second parent of node number 1 will be the first parent of node number 1. That is, it will be up of 1, 0, 0. That's what I want to say. So if I have this parent, which is the first parent of node number 1, which is -1, okay, but we can see that this is not a valid parent, it is -1 here. That means we do not have to fill these numbers, we just put -1 here. We don't have any valid parent for all of these nodes, because we can see that even node number 1 do not have a valid direct parent. So this equation do not make sense for node number 1. Now let's find the ancestors for node number 2. So let's find the ancestor for node number 2, the 2 raised to the power 1, that is the second ancestor, or the node which is 2 levels up from node number 2. Okay, so how we can do that? To do so this is what I want to find. For node number 2, find the ancestor which is 2 raised to the power 1, that is 2 levels up. So to do so, I need to find the ancestor which is 2 raised to the power 0, 1 levels up, and then for that ancestor, for that parent, find the parent which is 2 raised to the power 0, that is 1 level up. So to find the second parent, the second ancestor, the node which is 2 levels up from node number 2, find the immediate parent and then find the immediate parent of that node. That's what I want to do. Okay, so the immediate parent for node number 2 is 1. So move to 1. The immediate parent of node number 1 is -1. So put -1 here. Since the node which is 2 levels up, we do not have any node which is 2 levels above node number 2, will not have any node which is 4 levels above or 8 levels above. So we'll have -1 here, we'll have -1 here. So let's do the same for node number 3. Let's find the ancestor which is 2 levels up from node number 3. Okay, so from node number 3, I want to find the ancestor which is 2 levels up. This will be same as for node number 2 because they are siblings. So it will be -1, it will be -1, it will be -1. Let's prepare for node number 4. So for node number 4, I want to find the ancestor which is 2 levels up, and that can be found by by calculating the very the direct parent of node number 4. So I want to find, so let's write it down. So for node number 4, I want to find the 2 raised to the power 1, which is second parent, or the node which is 2 levels up. This can be found by finding this one, which is the direct parent. Okay, the node which is one level above node number 4, and that is node number 3, and it is given here. Up of 4 0 is 3. So now move to 3, which is here. Now for this 3, find the node or the direct parent of node number 3. That is, this is 3. So find up of 3 0. Up of 3 0 is 1, which is this node. So you're noticing how we are jumping. I want to find the first parent of node number 1. So are you noticing how we are filling this array? I want to find the node which is 2 level up for node number 4. To do so, I first find the node which is just above node number 4, which is 3. Then for node number 3, find the node which is just above node number 3. So this will be my answer, which is 1. Now let's find the node which is 2 raised to the power 2, which is 4 levels above node number 4, and that will definitely be minus 1, because from node number 4 I will move to node number 3. Then from 3 I will, because from node number 4 I will move to this node, which is like I want to find, what I want to find is so for node number 4, I want to find the 2 raised to the power 2, which is fourth parent. Okay, or let's say for node number 4, I want to find the fourth parent. So 4 2, the value here, and this can be found by finding the value which is up 4 1, and that is this one. And from this value, make a jump of 1. So from 1, move here. So from node number 4, I moved to the node which is 2 levels up. From 4, I moved to the node which is 2 levels up, which is this one, node number 1. So from this node, from 4, so basically I want to find the node which is 2 raised to the power 2, that is 4 levels up. So do so, I move to the node which is 2 levels up. Okay, so I move to this node, and this is here. Now from this node, move to the node which is again 2 levels up. So 4 levels is divided into 2 plus 2. Okay, make a jump of 2 from 4 to 1, then from 1 make a jump of 2, and this is minus 1, because 1 1, this will be 1, and 1 1 will give me minus 1. Okay, so the answer for this is minus 1. 4 2 will be minus 1, and so it will be for this one as well. So let's fill the array for 5 1, that is from node number 5. I want to find the ancestor which is 2 levels up, that is 2 raised to the power 1, and that can be found by finding the ancestor which is 2 raised to the power 0, that is 1 level above node number 5, which is 3, and then from this node find the ancestor which is again 1 level above it, which is 1. So for 5 1, the answer will be 1. Similarly, for 5 2, that is I want to find the ancestor which is 8 level above node number 5. To do so, I will find the which is not 8, which is 4 levels above node number 5. To do so, I find the ancestor, I will find the ancestor which is 2 levels above. So look at this one, this cell, and which is node number 1. So make a jump of 2, and that will direct us to node number 1. Now from node number 1, move again 2 jumps above this node, and that will be -1. From node number 1, I can see 1, 1 is -1. So it will be -1 here. And so it will be for this as well. So that's how I prepare my up array. This array will be used to perform the necessary actions which I require, that is used to perform the queries. So let's see how we can perform those queries. So let's take one query which is 4 3, that is start from node number 4. Okay, start from node number 4, find the ancestor which is 3 levels above it. So from node number 4, find the ancestor which is 3 levels above it. To do so, divide this 3 into 2's powers. So largest 2's power is 2 raised to the power 1, and then plus 2 raised to the power 0. That will be 2 plus 1. Okay, so let's first make this jump, that is the jump of size 2 from node number 4, right? From node number 4. So start from node number 4, make a jump of size 2, which is node number 1. Okay, so start from node number 4, which is this node. To make a jump of size 2, move to this column number 1. So 4 1, that is 1. Okay, so I get node number 1 here. I hope you are following me. So from node number 4, make a jump of size 2. So I am here at this point. Now from this node, which is node number 1, make a jump of size 1. Okay, and that is given at this position 1 0, and it will be -1. I hope you're getting it. I need to pay attention to this subscript. Okay, I need to pay attention to this subscript. So first find the value at 4 1, at value 4 1, row number 4, column number 1. This is row number 4, this is column number 1, this one, and the value is 1. Now from this value, now the row number becomes 1. Move to this row. Okay, move to this row, and from this row find the value at this column, which is column number 0, and that is -1. So the answer for this query is -1. I hope you're getting it, how we are making the jumps. Okay, so in this fashion, I will basically jump over the tree, and the time complexity for this is, for each query is log of n. Okay, that's the time complexity, because these are the maximum number of jumps which we can make, right? Okay, so that's the thing. So what is the equation? The equation to make the binary jumps is, so first of all, let's see the equation to build this table. That is easy. Basically, we iterate over all the rows of the given matrix. So we have n rows, and for each row we iterate over all the columns. We have log of n columns, and for each row ij, while I am building that matrix, I have up of ij is equals to up of I j minus 1 and j minus 1, right? So this is the equation to build the table, to build the matrix, right? Now let's write the equation to jump starting from a particular node, let's say some node. So to do so, what I will do is, the equation is simple. Just find the largest power of the given jump size. So we want to find, the let's say kth parent. So if I want to find the kth parent, so find the largest find the largest power of k, the largest power of 2 in k. That can be found like this. Let's say this is I. Okay. Now I found the largest power of 5. This is the jump which I will make. Okay. And that means move from the node, which is the starting node represented by this node variable, to this I. That means I am moving to 2 raised to the power ith ancestor of this node, right? And now from this k, which was the initial jump size, the initial ancestor, the number of levels up which we were given, from this k subtract this k minus is equals to 2 raised to the power I. So do it like this, and now we have k remaining. Now again find the largest power of 2 in this k and again make the jump. So in this fashion you will keep moving up. So the equation is simple. For the node, just move up from this node I levels, that is 2 raised to the power I levels, 2 raised to the power I levels. Okay, so this is the equation, and I will do this till I becomes 0. So initially I was this, now it will be, now we'll have new k. Let's say we had k, initially we had k to be 7, then take out the largest power of 7, which is take out the largest power of 2 in 7, which is 4, and the power is 2 because 2 raised to the power 2 is 4. So k, so here I becomes 2. So first we find the node which is 4 levels up, and then we find the ancestor which is 2 levels above the new node. Then we find the ancestor which is 1 level above the node, and finally we get the ancestor which is 7 level above the node from where we started. Okay, so that's how we're going to solve this problem. I tried to explain this solution using binary lifting, and I hope you got it. If you have any doubts, then please do comment down, and please do let us know how we can improve upon these videos and its quality. So let's just declare a up array. So first of all, let's declare an upper bound. The maximum number of nodes which we can have is 2 into 10 raised to the power 5. Let's declare the m value, which will be log of this max n, which will not exceed 20. Then let's create an array, up array, of dimensions max n into n, initialize it with 0. Let's declare an array which is level array of dimensions max n, initialize it with 0. Now let's create a DFS function to first store the immediate parents of each node of the tree. So node parent and the adjacency list. So for this up matrix, store the immediate parent here. And for this level, so we also have the third variable, which is the current level that we have. So for this level, for this node, we store this level. Now iterate over the child node. If this child is not equal to the parent, then recursively call this DFS function for this child node, and then we have our parent and this current node, and then we'll pass the adjacency list, and then the level will increase by 1. Fine. Now let's pre-process the matrix. Less than max of n, iterate over all the rows, and for each row iterate over all the columns, and find the parent for node number I, which is at j minus, it is at 2 raised to the power j minus 1th level up, if this, if we have a valid parent, if it is not equal to -1. Okay, -1. Then find the parent and then for the current parent which we are looking for, will have like this. Okay, so to find the 2 raised to the power jth parent or ancestor for node number I need to find the 2 raised to the power j minus 1th ancestor, and then the okay, so that's how it basically works, right? Okay, fine. So that's how we pre-process our matrix, that is this up matrix, and then for each query we have two things, that is x and k, x and then input k. Now check if the level of x is less than k. In that case, we'll never have a valid parent, so print -1 and continue right from here. Otherwise iterate till this k is greater than 0. Find the largest power of 2 in this k and then jump to that level. So x becomes up of, from this node which is x to I, and then from k subtract this 1 raised to the power 2 raised to the power I. Fine. So that's how you make these jumps, and finally in this x you will have your final ancestral node stored, which you will print here. Okay, so let's call this function here the DFS function from node number 1, then pass -1, then pass this, the third variable is the graph, and then the fourth variable is the level, which is 0. Then call this preprocess function, and let's see. Okay, it gave me right answer for this test case. Let's try to submit this one. Let's so let's try to submit this code. Okay, it got accepted, and I hope you learned something new. If you like the explanation, then do hit the like button, and make sure to subscribe to the channel and stay tuned with me, and I will see you soon in my next video.